Hi, let's continue our discussion of quantum dynamics. In this class, we shall discuss energy eigenkets. Here is a quick summary of what we have seen so far. This is the definition for the time evolution operator. The time evolution operator u of t, t0 relates the state of the system at an initial time t0 to the state of the system at a later time t. And we saw that the time evolution operator has to obey a differential equation. We called it the Schrodinger equation for the time evolution operator. Here is the Schrodinger equation for the time evolution operator. We looked at different solutions, different formal solutions to the Schrodinger equation for time evolution operator. And in the case where the Hamiltonian is independent of time, the solution takes the simple form. Okay, in that case, we can write u of t, t0 is equal to exponential minus I h t minus t0 divided by h bar. What we need to understand is how a state ket evolves in time. For this, we have to evaluate the effect of the time evolution operator on a general initial ket, say ket alpha. Now, for this, you may remember that given any ket, we can always expand it in a chosen basis. Okay, we have also said that the eigenkets of an observable always form a basis. So the basis that we use in quantum mechanics are eigenkets of Hermitian operators, which actually represent observables. For example, if A is a Hermitian operator that represents an observable, then the eigenkets, the set of eigenvectors of this Hermitian operator, can be chosen as the basis. Okay, and then this CA prime can be found by this relation. CA prime is equal to bar A prime ket alpha. All right. So you can think of it as the projection of ket alpha along ket A prime. So to understand the effect of the time evolution operator on a given state ket, what we need to understand is the effect of this time evolution operator on the base vectors or on these eigenkets of whichever Hermitian operator we are talking about. Okay. So what we need to understand now is the effect of the time evolution operator on the base kets. This is particularly straightforward if the base kets used are eigenkets of an operator A such that A commutes with the Hamiltonian. In this case, the eigenkets of A are also eigenkets of the Hamiltonian. We shall call this as energy eigenkets and we shall denote the eigenvalues as EA prime. Okay, so the eigenvalue equation for the Hamiltonian is given by H acting on ket A prime is equal to EA prime multiplied by ket A prime. So let me break it down for you. If the eigenvalue equation for operator A is given like this, A acting on ket A prime is equal to A prime multiplied by ket A prime. And if the Hamiltonian commutes with the operator A, okay, if the Hamiltonian commutes with operator A, then these kets are also eigenkets of operator H. The eigenkets of A are also eigenkets of operator H, which means that this ket A prime will satisfy an equation of the form H acting on ket A prime is equal to a number multiplied by ket A prime. This number we shall denote as EA prime. These are called the energy eigenvalues. Okay. Now we have already seen this property, we have already discussed this property when we talked about compatible observables. We said that compatible observables can be diagonalized simultaneously, right? It's the same thing here. Okay? So if two operators commute, they have common eigenkets. So we can choose a basis such that the basis vectors are eigenkets of both operators. The proof of this is quite simple, especially in the case where the eigenvalues are degenerate. All right, so just for the sake of completeness, let's prove it here also. We have already seen the proof, I think, but let's prove it again for more practice. Okay. All right, so let's start with this eigenvalue equation. A acting on ket A prime is equal to A prime multiplied by ket A prime. Okay, let's also assume that A commutes with the Hamiltonian. All right. Now, in this case, for simplicity, let's assume that the eigenvalues of A are non-degenerate. What do we mean when we say that the eigenvalues are non-degenerate? What we mean is that corresponding to one eigenvalue, there's only one eigenket. All right. So corresponding to the eigenvalue A prime, there's only one eigenket, ket A prime. If there are more than one eigenvectors corresponding to an eigenvalue, then we say that the eigenvalue is degenerate. All right. So let's assume that eigenvalues are non-degenerate. Then the proof is quite simple. Okay. Let's look at the proof. So assumption is that H and A commute. So we can write HA is equal to AH. All right. Now let's introduce a ket A prime on the right side. So we get HA acting on ket A prime is equal to AH multiplied by ket A prime. Okay. Or we can write this as, since this gives the eigenvalue equation, we can write this as H, or using the eigenvalue equation, we can write H multiplied by A prime acting on ket A prime is equal to AH multiplied by ket A prime. Okay. Now, since this is a number commutes with any operator, so we can write this as A prime multiplied by H ket A prime is equal to A multiplied by ket AH multiplied by ket A prime. All right. Now, if you look at this, we can write this equation as A. All right. I'll write this first. A multiplied by H ket A prime is equal to A prime multiplied by H ket A prime. Now we see that this indeed is again the eigenvalue equation for operator A. It's the same kind of eigenvalue equation that we have here. All right. We have got A acting on a ket, giving you a number multiplied by the same ket. Now we assumed that the eigenvalues are non-degenerate, which means that there is only one eigenket corresponding to a given eigenvalue. All right. This means that ket A prime and H acting on ket A prime have to be the same, or they could be multiples of each other. So in general, we can say that H acting on ket A prime has to be a multiple of ket A prime. Right. So this multiplicative factor we call as EA prime, and indeed this is the eigenvalue equation for the Hamiltonian operator. Okay, so we see that if A and H commutes and A satisfies this eigenvalue equation, then H satisfies an eigenvalue equation of this form. In other words, ket A prime is a common eigenket for operator H and for operator A. Now the reason why we are allowed to use a multiple here is because if you have this eigenvalue equation, then any multiple of ket A prime also satisfies the same eigenvalue equation. Okay, so that's why we say that because the eigenvalues are because the eigenvalues are non-degenerate, there is no degeneracy. All right, and since H acting on ket A prime satisfies exactly the same eigenvalue equation as equation 1, ket A prime or H multiplied by ket A prime has to be the same as ket A prime, or it could be a multiple of ket A prime. So in general, H acting on ket A prime has to be a multiple of ket A prime. In other words, ket A prime is also an eigenket of the Hamiltonian if A commutes with H. Okay. Now, if the eigenvalues are degenerate, we can still prove that, right? We can still show that you can choose a basis in which the basis vectors are common eigenkets of both A and H. All right. So, in a nutshell, to summarize, if A and H commute, all right, we can, whether the eigenvalues are degenerate or non-degenerate, we can always choose a basis which are common eigenkets of A and H. Okay, this is the important point. So let's choose the eigenkets of operator A as the eigenkets. Let's assume that operator A commutes with the Hamiltonian, which means that these are also eigenkets of the Hamiltonian. All right, so these eigenkets are also energy eigenkets, and they obey the eigenvalue equation H acting on ket A prime is equal to EA prime multiplied by ket A prime. All right. Now we can expand the time evolution operator in terms of ket A prime, bra A prime. We have seen when we discussed the matrix representation of operators that we can expand any operator in terms of ket A prime, bra A prime. All right. Now we shall also take T0 equal to 0 for simplicity. So you take our time evolution operator and put t0 equal to 0, and it becomes exponential minus I ht divided by h bar. Now let's introduce identity operators on both sides. We write the identity operator in terms of the completeness relation. Right? The identity operator equal to sum over a prime, get a prime, bra a prime. This is what we called the completeness relation, right? Which is quite useful, as we have seen many times. Here also we shall use it. We introduce an identity operator on the left and an identity operator on the right. Okay. So this is the identity operator on the right. Sum over a prime, get a prime, bra a prime. This is one identity operator, right? And here we have sum over a double prime, get a double prime, bra a double prime. So we have inserted two identity operators, right? Now let's look at this term, exponential minus I h t divided by h bar acting on get a prime. So let me write that term here, exponential minus I h t divided by h bar acting on get a prime. We can now use the power series expansion. So we can write this as the identity operator plus minus I h t divided by h bar, okay, plus minus I h t divided by h bar whole square plus etc. So there's a 1 by 2 factorial here, 1 by 2 minus I h t divided by h bar whole square plus etc. acting on get a prime. Now we can use the fact that get a prime obeys this eigenvalue equation. Alright, so time is just a parameter. So h acting on get a prime can be written as e a prime get a prime. Alright, so the identity operator does not change. Here we have got minus I e a prime t divided by h bar multiplied by get a prime. We shall retain get a prime outside here. Right? We are just using the relation h acting on get a prime is equal to e a prime multiplied by get a prime. And here we have got the Hamiltonian acting twice on get a prime, and obviously that should be 1 by 2 minus I e a prime t divided by h bar square plus etc. Okay, acting on or multiplied by get a prime. Now what do we have here? This is again a power series expansion for the exponential. All right, what we have here is again a power series expansion for the exponential, which is clearly exponential minus I e a prime t divided by h bar. Okay, so what are we saying here? What we are saying here is that exponential minus I h t divided by h bar acting on get a prime can be written as exponential minus I e a prime t divided by h bar multiplied by get a prime. Okay. In general, you can remember this. If you have an exponential of an operator acting on the eigenket of the operator, then you can also always write this as exponential of the eigenvalue multiplied by the eigenket. Okay, so if this works, if what we have here is the eigenket of the operator in the exponential, then you can write it as the exponential of the eigenvalue multiplied by the eigenket. Right, you can remember this. So from here we have exponential minus I h t divided by h bar is equal to sum over a prime, sum over a double prime, get a double prime, bra a double prime. Okay, this is exponential this becomes exponential minus I e a prime t divided by h bar acting on a prime. So let me just write it here. This becomes exponential minus I e a prime t divided by h bar acting on get a prime. Now this is a number. All right, there is no operator. This is just a number. You can take it to you can take it outside. All right, so I'll take this number to the right side of this get, and what we are left with is sum over a prime, sum over a double prime, get a double prime, bra a double prime, which is all here. Now let me write this get a prime in here. All right, and then the eigenvalue exponential minus I e a prime t divided by h bar. We also have a bra a prime in here. All right. Now we can use the fact that the eigenkets of an operator, let's say the eigenkets of an operator forms a complete orthonormal set. We can also always choose this basis to be an orthonormal set. Okay, so we shall always work with orthonormal sets. All right, which means that bra a double prime get a prime is equal to delta A double prime A prime. Okay, so let me remove this here and write delta A double prime A prime. Now we can carry out the sum over A double prime. Here is the Kronecker delta. So if you sum over all A double prime, the only non-zero value in the sum is where A double prime is equal to A prime. So instead of this summation and delta A double prime A prime here, we can just write one term where A double prime is equal to A prime. So this summation becomes sum over A prime. This summation goes, this delta A double prime A prime also goes, and wherever A double prime appears, you can write A prime. So this becomes get A prime exponential minus I e A prime t divided by h bar and then bra A prime. That's what we have here. Okay, so we can write exponential minus I h t divided by h bar is equal to sum over A prime get A prime exponential minus I e A prime t divided by h bar bra A prime. Okay. Once you write the time evolution operator in this form, we can solve any initial value problem, right? We mean by any initial value problem, we mean that once you know the initial state, all right? Once the initial get is known, using this form of the time evolution operator, you can find the get at any time, right? The only thing you need to know is the expansion of the initial get in terms of the basis, in terms of the same basis. All right. So once you know the expansion of the initial get in this basis, something like so, right? Get alpha equal to sum over A prime, C A prime, get A prime. If you know these expansion coefficients, you can just apply this form of this operator on the left and find the get at any time. Okay. As an example, suppose that the initial get expansion reads get alpha comma t0 equal to 0 is equal to sum over A prime get A prime bar A prime get alpha. Okay, now this bra A prime get alpha are called the expansion coefficient C A prime. So we are writing get alpha comma t0 equal to 0 is equal to sum over A prime C A prime get A prime. Okay, what we have done here is that we have simply expanded the given initial get in terms of these basis vectors. In terms of these basis vectors. Right, and what's the specialty of these basis vectors? These are simultaneous eigenkets of operator A and operator H. All right. Okay. Then we can find this is the state at the initial time expanded in terms of the energy eigenkets. Now we can find the state at any later time. All you have to do is to apply the unitary time evolution operator to the left, the time evolution operator to the left of this initial state get. So we'll write the state at a later time like this, get alpha comma t0 equal to 0 at a later time t. We are just following the notation that we fixed in the beginning. So get alpha comma t0 equal to 0 at time t is the state of the system at a later time t. This is equal to u of t comma t0 acting on get alpha comma t0 equal to 0. Okay. Now since we have expanded the initial get in terms of energy eigenkets, we can use this form of the expansion, this form of the time evolution operator. The form of the time evolution operator we obtained in the previous slide is sum over A prime get A prime exponential minus I e A prime t divided by h bar and then bra A prime. Okay, this is u of t comma t0. Now you just act it on the initial get alpha comma t0 equal to 0. All right. Now this is equal to, what is this? You look at this. This bra A prime get alpha is what we call C A prime. So this is simply C A prime that we fixed earlier. All right. So this is equal to sum over A prime get A prime C A prime exponential minus I e A prime t divided by h bar. All right. So this is the expansion of the state of the system at a later time in terms of the same basis get A prime. So let me repeat what we have here. We have the expansion of the initial state in terms of this basis set. All right. Here what we have obtained is the expansion for the state at a later time in terms of the same basis. All right. But the expansion coefficients now are Ca prime multiplied by exponential minus Ia prime t divided by h bar. So initially the expansion coefficients are just Ca prime. At a later time the expansion coefficients have changed to Ca prime exponential minus Ia prime t divided by h bar. Okay. What we have seen is that if the base vectors that we choose are also energy eigenkets, then the time evolution can be represented quite in a simple manner. All right. So what we have seen is that initially, if the state is given by get alpha comma t0 equal to 0 equal to sum over a prime, let me write this as Ca prime of 0, get a prime. All right. So this is the expansion of the state at time t equal to 0. Then we saw that the state at a later time is given by sum over a prime Ca prime of t multiplied by get a prime. The only change is the modification to the individual expansion coefficients. That's the only change, right? And this change is also simple. What's the relation between Ca prime of t and Ca prime of 0? We saw that Ca prime of t is equal to exponential minus Ia prime t divided by h bar multiplied by Ca. All right, so the individual expansion coefficients simply get multiplied by a phase factor. Right, so that's what we say here. Ca prime at t equal to 0 goes to Ca prime of t, and Ca prime of t is equal to Ca prime of 0 multiplied by this phase factor. It just picks up a phase factor. Individual expansion coefficients just pick up a phase factor. All right. Now, since these are just phase factors, you see that the modulus of individual expansion coefficients remain the same. We know that the modulus of individual expansion coefficients are related to the probabilities for measuring individual uh, values, all right, or these are related to the probabilities for individual measurements. So what we see is that the probabilities for measuring energy, particular values of energy or particular values for the observable A remain unchanged with time. All right. Now this is only true if the base vectors are also energy eigenkets. All right. So if the base vectors are also energy eigenkets, describing the time evolution of the system or finding the time evolved state becomes quite easy. All right. So we actually see that these expansion coefficients oscillate in time. All right. This is an oscillatory thing. It oscillates in time. All right. And we see that the relative phases among various components vary with time because the oscillation frequencies are different. Okay. So if you look at it as an oscillation, we see that individual expansion coefficients oscillate differently with respect to time. All right, because the oscillation frequencies for each base get is different. Okay, these are the oscillation frequencies. Right, so if you think of this as an oscillation, we can say that the relative phases among various components vary with time because the oscillation frequencies are different. So you can think that the individual expansion coefficients oscillate with different frequencies as time evolves. All right, so individual expansion coefficients are just oscillating uh, with different frequencies. All right. Now let's look at a special case where the initial state happens to be one of the base gets itself, one of the eigengets get A prime itself. All right. So we are looking at the case where get alpha comma t0 equal to 0 is simply one of the eigengets of operator A or one of the base gets that we are considering here. All right. Now, for example, this could be the case immediately after the measurement. Suppose you measure the energy of a system. Immediately after the measurement, we know that the state of the system will be one of the energy eigenkets. All right? Or if you measure the observable A, immediately after the measurement, the state would be one of the eigenkets of operator A. Suppose we are starting with such a state. All right? What can we say about the time evolution? So the initial state is get alpha comma t0 equal to 0 is equal to get A prime. So again, if we choose this as the basis, we see that the expansion coefficient here is 1 and the expansion coefficient corresponding to other base vectors is 0. All right. Now what happens at a later time? The expansion coefficient simply changes to exponential. So let me write as 1 multiplied by exponential minus Ia prime t divided by h bar because each expansion coefficient just picks up a phase factor. right? Since all other expansion coefficients are 0 initially, they remain 0. All right. So the state at a later time, which we write as get a prime comma t0 equal to 0 at a later time t, is get a prime multiplied by this phase factor. All right. Now we see that initially this is an eigenket of operator A with eigenvalue A prime. This is also an eigenket of the Hamiltonian operator with eigenvalue E A prime. All right. We see that at a later time also there are eigenkets of A and H with exactly the same eigenvalues. All right. Because here the initial eigenket has been multiplied by a number. The eigenvalue equation does not change, right? Because if A acting on A prime is A prime multiplied by get A prime, then A acting on exponential minus IE A prime t divided by H bar multiplied by get A prime is also, since this is a number, it comes out. So you can write this as exponential minus IE A prime t divided by H bar, A acting on get A prime. Again, using the eigenvalue equation that we have here, this becomes A prime multiplied by get A prime, or we see that this is equal to A prime exponential minus IE A prime t divided by H bar multiplied by get A prime. So this thing is also an eigenket of operator A with the same eigenvalue A prime. Right? In the same way, this is also an eigenket of the Hamiltonian operator with the same eigenvalue E A prime. So if the system is initially a simultaneous eigenstate of A and H, it remains so at all times. So if you start with a state which is a simultaneous eigenket of operator A and the Hamiltonian, it will remain so at all times. All right. So the most that can happen under time evolution is that it just gets multiplied by a number, a pure phase factor, get A prime. All right. Now, if get A prime is an eigenket of operator A with eigenvalue A prime, then so is this thing, because this is just a number multiplied by the same ket. Right? This is also an eigenket of operator A with the same eigenvalue A prime. So we see that the eigenvalue A prime does not change with time. Right? So it is in this sense that we say that an observable compatible with the Hamiltonian is a constant of the motion, does not change with time. Now, in general case, we can also show that the expectation value of operator A or expectation value of observable A will not change with time because the individual probabilities do not get modified, right? Because each of the expansion coefficient is just getting multiplied by a pure phase factor whose modulus is 1. So the individual probabilities do not get modified. So in general, we can actually say that the expectation value of the operator A also remains unchanged, does not change with time if operator A commutes with the Hamiltonian. Right? So in this sense, we can say that an observable that commutes with the Hamiltonian is a constant of the motion. We shall encounter this connection once again when we discuss what's called the Heisenberg equation of motion. At that time, we'll also make a connection with the classical mechanical case where we formulated these conservation laws in terms of Poisson brackets. Right? But that's for a later class. So we have reduced the task of quantum dynamics to finding an observable that actually commutes with the Hamiltonian and evaluating its eigenvalues. Right? Once this is done, we just expand the initial ket in terms of the eigenkets of that observable which commutes with the Hamiltonian, and then just apply the time evolution operator. And the action of time evolution operator, as we said, is simple. It just results in individual expansion coefficients picking up an extra phase factor. So far, we talked about the case where there is just one observable A that commutes with the Hamiltonian. But the same ideas can be generalized to the case where there are several mutually compatible observables which also commute with the Hamiltonian. By this we mean, suppose there are several observables, several Hermitian operators, several observables which all commute among themselves. All right? If you take operators A, B, and C, and they all commute among themselves, right? The commutator of A and B, the commutator of B and C, the commutator of A and C, these are all 0. In addition, each of these operators also commute with the Hamiltonian. Okay. In this case, we know that the operators A, B, C, etc. and the Hamiltonian have common eigenvectors. They have common eigenkets. We can denote these eigenkets using the eigenvalues of these operators. We can write this as ket A prime, comma B prime, comma C prime, etc. Or as we did in the first chapter, we can use a collective index K prime, right? So E K prime. So since K prime is a simultaneous eigenket of A, B, C, etc. and the Hamiltonian, right? These K prime are also specifically energy eigenkets. We can write H acting on K prime is equal to E K prime multiplied by ket K prime. Right? And E K prime is uniquely specified once all these eigenvalues are given. Now we can do exactly what we have been doing so far. We can choose the set ket K prime, which are also energy eigenkets, as our basis. Right? We use this as the base vector. We use this as the base vectors. And then just as before, we write the time evolution operator in this form. We write it as sum over K prime, ket K prime exponential minus I E K prime T divided by H bar bra K prime. Okay. Now we expand the initial state ket alpha in terms of the same basis. All right. Ket alpha is equal to sum over K prime, C K prime, ket K prime. Now, in order to find the state at any later time, you apply this operator to this state, okay? And we'll see exactly as before that the only thing that happens is that each of these expansion coefficients get modified, right? They just get multiplied by a phase factor, okay? So we'll see that the analysis is exactly the same. We'll see that Ck prime will evolve to Ck prime multiplied by exponential minus Iek prime t divided by h bar. Okay. This is why it's important to find a complete set of mutually compatible observables which also commute with the Hamiltonian. Right now, once such a set is found, we can express the initial ket as a superposition of the simultaneous eigenkets of A, B, C, and H. Right? That is, we can take the initial ket and represent it as sum over K prime, C K prime, ket K prime. All right. Now, since these are also eigenkets of the Hamiltonian operator, the state at any later time can be written as, okay, following the analysis that we already did, the state of the system at any later time can be simply written as sum over K prime, C K prime, exponential minus I E K prime T divided by H bar multiplied by ket K prime. All right. So we see that the initial expansion coefficients have been modified in such a way that each of the expansion coefficient is now multiplied by a phase factor. So the problem of dynamics is completely solved once we do this, right? Once we choose the correct basis, right? Once we choose a good set of basis vectors, all right? So in this manner, we can solve the most general initial value problem with a time-independent Hamiltonian. You remember that we have discussed only the case where the Hamiltonian is time-independent. So if the Hamiltonian is time-independent, the problem of time evolution or problem of dynamics is easily solved in this manner. We have discussed the problem of time evolution in quantum mechanics in the case where the Hamiltonian is independent of time. Let me summarize the main points. When the Hamiltonian is independent of time, we can write the time evolution operator as u of t comma t0 is equal to exponential minus iht divided by h bar. We have taken t0 equal to 0 or the initial time equal to 0 for simplicity. Okay. Now we found that solving the initial value problem is simple if we choose base vectors in such a way that the base vectors are also energy eigenkets. All right. So we just have to choose base kets which are also energy eigenkets. All right. So we choose base vectors which is denoted by the set K prime in such a way that the Hamiltonian acting on ket K prime gives you E K prime multiplied by ket K prime, where E K prime are the energy eigenvalues. Now, how do we construct such a basis? In order to construct such a basis, we have to find a complete set of mutually commuting observables which also commute with the Hamiltonian. Right? So we have to find a complete set of observables which satisfy these relations. A comma b has to be equal to 0. Okay, or a comma b is equal to b comma c is equal to c comma a, etc. Right? All these have to be equal to 0. Then we say that these are mutually compatible. In addition, we need each of these to be commute with the Hamiltonian also. Okay. Now, in this case, these operators A, B, C, etc. and H, they have common, can be shown that they have common eigenkets. Right? Now we label these eigenkets by the eigenvalues of each of these operator. Okay, we can label the eigenkets as get A prime, comma B prime, comma C prime, etc. Or we'll use a collective index get K prime. Right? So that's the collective index that I have used here. Now, once we have such a basis, we can expand the initial get in terms of these base vectors, right? Sum over k prime, ck prime, get k prime, all right? Where ck prime are the expansion coefficients which can be found by bra k prime get alpha, all right? Where get alpha is the initial get. Now, in order to find the get at a later time, get alpha comma t0 equal to 0 at time t, right? You just apply the time evolution operator on the initial get, right? So you can write this as u of t comma t0 acting on get alpha or get alpha comma t0, all right? Now we can use this expansion and this form of the time evolution operator, all right? So we can write this as this is equal to exponential minus iht divided by h bar acting on sum over k prime ck prime get k prime. Okay, so here we have got a linear combination of all these base kits, right? And ck prime are the expansion coefficients. Now this is an operator, ck prime is a number, so we can take this inside. So this becomes sum over k prime ck prime exponential minus iht divided by h bar acting on get k prime. Now since get k prime are also eigenkets of the Hamiltonian, we can write this as sum over k prime ck prime exponential minus I e k prime t divided by h bar multiplied by get k prime. Okay, we have just used the eigenvalue equation. H acting on get k prime is equal to e k prime multiplied by get k prime. Okay, so even if you have this operator in the exponential, we can use the eigenvalue equation. We showed that using the power series, we can write this as, and also using the eigenvalue equation, we can write it in this form. All right, so what we see is that the initial ket is given by sum over k prime ck prime get k prime, and the ket at a later time is now given by sum over k prime ck prime exponential minus I e k prime t divided by h bar get k prime. So the time evolution, the problem of time evolution is easily solved, all right, because the only thing that's happening here is that the expansion coefficients, right, at time t equal to 0 become ck prime exponential minus I e k prime t divided by h bar. Okay, in other words, we can simply write the time dependence of the expansion coefficient as ck prime of t is equal to exponential minus iht divided by, minus I e k prime t divided by h bar multiplied by ck prime of 0. Okay, so the only thing that's happening during the time evolution is that the individual expansion coefficients get modified. All right, they just get multiplied by a pure phase factor of this form. So in this way, we have solved the initial value problem. Okay. We also notice that the modulus of the individual expansion coefficients do not change. So the probabilities for each measurement outcome of energy or any of these compatible observables, these probabilities do not change with time. We also considered the case where the initial state is an eigenket of an observable that commutes with the Hamiltonian. In that case, we saw that the eigenvalues do not change with time. In other words, we are talking about an operator, an observable that is constant of time. Okay, so we also saw the fact that if an operator or if an observable commutes with the Hamiltonian, okay, then this observable is also a constant of motion. So these are these are the things that we discussed in this session. I hope you have followed the class. I shall wind up for now. Thank you.